Hello everybody and welcome to robot build log number 8. So I've made quite a bit of progress on the electronics part, or the programming communication part, and I was getting a little bit bored and was hitting a couple walls. So I decided just to jump into some of the mechanical stuff. I'm at home right now and I have access to my 3D printer and all my tools and everything, so it's a perfect time to take advantage of that. So what I'm going to do is build a lot of this out of scavenged materials. I take apart printers for fun to kind of see how they work and to scavenge materials and stuff like that. So I've got a whole bunch of these DC motors kicking around. And what I did was I went through and I tested all of them with my multimeter. And I hooked them up to the battery and I wrote on each one of them what the running amperage was and what the stall torque was, or the stall amperage was. So I could see how much power my motors would consume. Now I plan on using one of these little motor drivers. They're pretty common. This is an OSEP motor driver, and it can run one stepper motor or two DC motors. These are obviously DC, like I said, so this will actually be able to run two motors, and I want to use one for left and one for right on each one of my tracks. So I think these can put out 2 amps each, like on each side it can do 2 amps. So that was what I was going for when I wrote down all the amperage ratings. So if I'm driving my robot and it like hits something and it stalls out or it's trying to go up a really steep hill, that is the maximum amperage it's going to be running through the motor, and I won't burn out my little driver because, well, obviously the motor won't pull that much. So I went through them all and I tested them all, and I found 2 that would work for me. And I happen to have 2 printers that I took apart in the past that were both HP and both were the same motor. So you might recognize this part. Not quite sure how it goes. I think it goes like that. This is the inside of a printer. This kind of goes back and forth like this with your print cartridge on it, and that's what, you know, draws on the paper. And this is just a little motor that drives this belt, which makes this move back and forth. So I have 2 of these and they're perfect. When it's just running with no load, it's 0.08 amps, and if I pinch it and if I stop this thing from moving, the most it's going to draw is 1.7 amps. And they're pretty strong motors, and they're both exactly the same, so that was perfect for me for my uses, because I obviously want the same motor on each side. So that's that. So I've been ordering some supplies from AliExpress and Banggood and all that stuff. This is going to be the main beast battery that's powering the robot. It's a 14.8 volt 65C 2000 milliamp hour battery. So the 65C is kind of how much current it can put out. I think you multiply that by the voltage or something like that. I'm not even sure right now. But main thing is it's 14.8 volts, so that's a little bit higher than your average 12 volt. And it'll run at an amp for 2 hours, or run at 2 amps for an hour. So that should be enough to probably run my whole machine for maybe half an hour if I'm moving around and using different electronic components and stuff. So that's that. This is a little test rig I rigged up. So this is the other motor. Now I told you guys I had 2 motors. This is the one that I already took off. It's exactly the same as the other one. And right now you'll see I've got this tape on it. So I'm going to show you how I test how fast this motor goes, so then I can design the gear train. And this gear right now, it's not obviously connected to anything. I'm just showing you, like, it's a PLA printed gear. The PLA is the plastic. Normally I use ABS, but I just switched to PLA, and this stuff prints so nicely. I'm just amazed. So anyway, back to this. So this is just a little taped impeller I put on there, or not impeller, it's just whatever. It's just tape on there. So I've got a little Arduino program that I'm going to use to figure out how fast this thing is spinning. So what's happening here is I have an optical encoder, and this is taken out of the printers just like a lot of my other parts. Here's a couple more. You know, I've probably got 15, 20 of these things just laying around. And how these work is, so it kind of looks like this thing. It's got on one side an LED, and it is shining onto this, I guess like a sensor. And this thing only senses IR light, and this is an IR LED. So when this LED shines on here, it's completing a circuit. And basically when there's nothing in this gap, it's going to put out a voltage. This is kind of how it hooks up. It's got a shared ground between the two sides, between the two little items here. It's got a 5 volt for the LED, and there's an output wire that will go to the Arduino, and that is like the signal wire off of this little sensor. So like I said, when the LED shines on it, it's going to complete the circuit, and it's going to put out a little bit of voltage onto this this pin on the Arduino. You also need to tie it down with a 10k ohm pull down resistor, just so it's not floating. If you don't have that there, it's going to give you just some wonky values because it's not always tied to positive or negative. It can just, you know, float there. So that's what this little device does. There it is again there, and I think you can see I've got it hooked up on my little Arduino breadboard. And what's happening is I actually just pulled this sketch from online. It's called a tachometer sketch basically. And what I'm going to do is turn this motor on, and as it spins, it's reading how many times and how fast, how often it's interrupting the beam. Alright? And in the code here, you basically put in how many little blades are on your spinning device, and it calculates, you know, how fast this thing is turning. So I'm going to fire this up and show you. I already know, you'll be able to see in the code, there's like a serial monitor that'll pop up. Actually, I can get that running right now. So this is constantly updating. It's not showing the numbers right now, it's showing 0 rotations per second, 0 RPMs, and the value is 0 because nothing's happening. But if I plug this wire back into the positive like it's supposed to be, let's see. There we go. Now it's doing its thing. So now it's chooching along. It's showing a value of 100, and that's an analog value. It goes up to 1023, and I've got it set in the code. I think my division is 60. Anything over 60 is going to be on. Anything under 60 is going to be off. So here we go. Let me plug this in. I don't have this hooked up with a switch yet because I'm fancy like that. There she goes. And so I'm just going to put this in here. Try not to hit it. And there we go. So it's showing 85 rotations per second, 5,100 rotation per minute, and it keeps popping off the value that it's showing at that second. The other gear is just spinning because it's on bearings. It's being blown. And this is a pretty steady steady motor. It's pretty much always at, you know, 5,100 plus or minus maybe 30 RPMs. Even if I put this on here and try to slow it down, it's pretty strong. Like, it only dropped to maybe, I think, 4,000 there. 3,500. So that's pretty good. I know that if I put a load on this, if I'm driving something, it's still going to work. Because once this is geared down to its final reduction, it's going to be pretty strong. So that's that. I'm going to peel the tape off here and show you this thing spinning. And while I do this, I'll just have a little chat. So I've got a little Excel program worked out right now, and I plan on using it to help me determine my final drive ratio. And actually, before I even made the program, I was kind of working on it, and I had it at like 0 or 1 to about 1 to 100. I thought that would be good because I thought this thing was going to be spinning at a much higher RPM. But after doing this little RPM test, I now know that it's only going at 5K, and I can actually reduce my gear reduction. So that's kind of good and bad. I was hoping it'd be a higher RPM, because if it's as hard as it is to stop it at the, you know, like 10,000 RPM, that means it's even stronger than what I expected. So, but anyway, it's still a pretty strong motor, more than enough to do the one side. Oh look, I have a knife right here. More than enough to do the one side of the tank if I've got another one on the other side. Alright, back here now. I just had to pause that and adjust some stuff here. So this is the spreadsheet I was just talking about, and I'm not going to get into detail, but basically what it allows me to do is define, like it's got a list of how many teeth are in a gear, and then it'll calculate the angle between teeth, the tooth center radius, which I think is called the pitch radius or something like that, then radius to the circle contact. This is all just kind of stuff for designing the gears in CAD. The way I designed them was I'm just using like a circle profile. It's not a traditional tooth profile. They're all just tiny little circles that will fit into each other, and it actually works pretty good, and it was easy to print with the printed plastic gears. Like I don't want to get too fancy and have teeth snapping off. So this little setup helped me do that. Now over on this side, I can put in like right now I've got 7 teeth on gear 1, 32 teeth on gear 2, and it calculates the basically like the ratio for those two gears. It calculates a shaft distance for when I'm modeling the housing, and like as I enter a bunch of them in, it'll add up the total ratio just to make things go a little bit smoother. Then over here I've got a little thing where it takes the final ratio here, multiplies it by my motor RPMs, multiplies it by the drive wheel diameter, and it'll give me an approximate speed that the robot will run at in the end. So right now what I've got planned out is doing my main sprocket will be 7, and then I'll do a bigger one with 32, and then on that one right here, this one is 7, but on my new design I'll probably do 9 and 31 again, or match these two for 31, 31. Anyway, this should give me a final speed of about 1.6, 1.7 meters per second, which is good enough for the robot I'm doing. I'd rather have more power than more speed, but I mean obviously you don't want it to be slow and boring. So anyway, that's that. I'm going to hook this guy up. These gears, they're going to be loud for sure. I think I'll be able to maybe quiet some of that down with housing, maybe some like noise deadening materials in the motor housing. I'll grease them up for sure, whatever greases I can use to use on plastic. I know some of them will dissolve the plastics and stuff like that, but I think from what I heard, just white lithium grease is pretty inert, or maybe some graphite or something like that. So that's something I'll be doing. But yeah, this is just a demonstration of how the gears work, and I'm actually super impressed with the 3D printed gears. So here's that. Right, so you can hear it going. It's a little shaky, but it's already hard for me to stop by hand. I'm more than confident in how much, let me get that. I'm more than confident in the power that this is going to have. That was pretty hard for me to stop, and that's just one side. There'll be 2 of these, and there's still another, I guess, what's my ratio here? Probably it'll be about 3 or 4 times stronger than what it is right now with my next step down in the gears. Anyway, I think that's pretty much it. Probably rambling on here, so I'll catch you guys in the next one. Thanks for watching.